Okie dokie. Well, thank you to Professor Carlo for having me out here. Like he said, I used to live in Dubai. It was my first place outside of my home country of the United States that I lived, so I have very fond memories of here. And he's shown you guys a project. You guys have just shown it to me. I really think it's cool to be able to come out here and work with you guys, at least for this weekend and a little bit into this week. Before we get going, I'm a structural engineer, and I'm very passionate about structural engineering. And I think whenever I talk to architects, I wish I could give this presentation, because I think it's very important in an industry like ours, which is very much a vertically disintegrated industry. In other words, you guys speak a different language, I speak a different language, human, like literally the language of design. Contractors speak a different language, clients speak a different language. It's really important to be able to communicate. Ipso facto, I'm working on my third language in Chinese, and I'm working on my fifth programming language right now. The more emphatic you can be in different languages, the more powerful you'll be, because this is an industry that really is all about communication. So I want to give you a bit about my background and give you some fundamental structural lingo and principles that you'll hear me talk a lot about. Equally, when we're talking, I need you guys to teach me a bit about your architecture and what you want. Somewhere in the middle, we'll find the answer to all of our problems. To give you a scale of things, it wasn't too long ago that I was at university. I studied in the United States, first at the University of Akron and then at MIT. And then I joined Bureau Happold, like I said, out here in Dubai, but then I moved to Hong Kong, where I've been ever since. And been doing some really, really cool work with them all over the world. So based out of Hong Kong. And I've found myself really blessed to be able to say that I've worked on projects in all of these different countries, traveling to many of them. And most of this was made possible by computational engineering. So I can't stress this enough. You guys already showed me. You guys are doing complex work. You need to be able to speak to the machine just as much as you need to be able to speak to human beings. I'm a firm believer that the only reason that I was able to, in this short period of time, work on ridiculously cool stuff like this is because I know how to interact with the machine better than most people in Bureau Happold, let alone outside of Bureau Happold. You really need to focus on both. There's not enough in this world anymore to just know I'm awesome at just architecture. You need that. That's a given. We expect that. But we need also more people who understand how to interact with the machine. And that doesn't mean going and saying, I know how to use Rhino manually. It just doesn't anymore. Some of my favorite projects are this one. This was my thesis. This is the Basilica of San Francesco in Assisi, Italy. It's a UNESCO World Heritage Site. In 1997, there was an earthquake that hit the basilica. It had been up for more than 850 years. 850 years, and this happened. There was some really, really important heritage that was lost, and 4 people died. Myself and some of the people at MIT, we said, but it's been there for 850 years. Why did it actually fall down after 850 years? It's no stranger to things getting hit, this thing getting hit by earthquakes. And it's an absolutely beautiful basilica, by the way, if you have a chance to go. Well, what we found is in about 1950, there was a beautiful wooden roof that you can't see in this picture that was above all these vaults that collapsed. And they decided, we can't have that anymore. They didn't know what they were doing back in the day, and we're going to replace that with reinforced concrete. So there was definitely a cause and effect that we were able to show that because you destroyed a roof that was 850 years old, which is automatically something you shouldn't be doing in the first place, you actually caused this to happen. That hit particularly home to me. It's really great to be a structural engineer sometimes when this is the house that my grandfather was born in and the house that I normally would spend my kids' summers in. And when I got the call to say our hometown had been hit by an earthquake, I was already there. And I was able to go and tell my family that our house, there was no helping it because right here, they had done the exact same thing to our home. Had we been in here, we probably would have lived, but we probably would have been severely injured. So that's really why, to me, I really love being a structural engineer, is because you actually can look at stuff like this and understand, nope, do not try and tell me you can fix that without taking the roof out. It's unfortunate, but no one died. And we can actually control how no one will die in the future when the earthquake eventually comes again. My second favorite project ever is Morpheus Tower. which is here on the left. And some of the work that I did on computational engineering we'll talk about tomorrow. Jason's familiar with it because he's seen me do the presentations in Hong Kong. And then my third favorite is XRL West Kowloon Terminus, which we might talk about tomorrow as well. But again, more really complex work if you're in Hong Kong and you have a chance to go see it. It's not the best architecture in the world, but it is something that is impressive from the idea of just complexity and how you actually deliver projects that are that big in the modern era. We'll talk about that stuff tomorrow. Okay, like I said, we need to talk the same language. So you have to understand where I'm coming from. And there are two golden rules of structural engineering. Rule number one, nothing can ever fall down. Ever, 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 ever. That is unacceptable, ever. Maybe something, never is a big word, but unless the nuclear bomb goes off, things should not be falling down, okay? Unless the worst typhoon in the world that has never been seen before is a complete anomaly, stuff should not fall down, and even then, it probably shouldn't fall down. So that is why I really, as a structural engineer, you do lose sleep sometimes, because that is on your shoulders. And it's usually on your shoulders from day one. You show up from this university setting, and you've been taught about engineering failures. And I'm very happy that as part of my training that I received this article that is always kind of in the back of my mind when I'm doing stuff. Because this article, and I'm happy to share it, it's something that kind of mixes science and humanity for me. And whenever I think about having to be there, if something of mine had problems, I always think of this particular story because that's what we deal with. I know we're in these nice studios and stuff like that, but we are building things that are very serious. The public safety has to come first. Speaking of public, the rule number two. Remember what I was saying, no one likes to be near things that bounce around or seem to be moving or it's dangerous? Yeah, that's rule number two. Now, it's not nearly as bad as rule number one when things go wrong on this one. But it is quite embarrassing, and it can cause people to die just as well. When you have situations like this, where people are actually causing the structure to move back and forth, you can cause a stampede of people, and people can die just because of that panic. So those are the two golden rules. Things cannot collapse, and things cannot move excessively. Obviously, with the big one on the first one. So that brings us to the next thing. What does it mean to make those things not happen? And for you not to have those things not happen, you have to understand something called capacity. My favorite question to ask architects to get them into the right frame of mind for what's coming next is if I give you this pen right now, and I ask you to break it, don't break it, but can you just mimic how you would break it in the most expedient fashion? For this short for the class. You throw it. No. So she's doing this. Does everybody else agree? Would anybody else try and do it any other way? We just, right? We do that. No one's going to try and pull it apart. That doesn't count. No one's going to try and no one's going to try and push it. No one's going to try and do this. Right? Okay. Good. Because we all live on the planet Earth since the day we were born. We all kind of understand inherently physics and how things break and how things work. But just so we be a little bit engineering here, that's only one of the ways of breaking stuff. And that's what we're in the business of in structural engineering. Not breaking stuff, but kind of making sure things don't break. You kind of have to know how things break before you can make them not. So you've picked bending, 1 degree of freedom. Very smart. We're going to tell you why scientifically that is soon. Tension, compression. No one said, oh, I'm going to torque this, right? Even though that would have been, you can actually torque this one and break it, quote unquote. Or shearing, which is basically the same thing as what you were doing, except for really not giving it any lever arm, right? So that is the fundamental atom of structural engineering. These are the way things break. Now, you say, well, Mita, that's nice, but we live in things that are not just one pen. We live in things that are like 10, 20 million pens connected to each other. And that's where you get down to load paths. At HKU, I know Holger turned me onto this book, Tragen System, Systemen. Very cool book. I really like this book, and I recommend it to you guys, like just to sort of get your head around what structural systems are. But But really what it comes down to me, is something that I don't want to scare us with math. There is a bit of stuff that we can remember that will help us. Very simple law. Force equals something called the spring constant times extension. Everything that is structural abides by this rule. There is a stiffness to the spring, and then there is a deflection. Both of those are related by how much force. It's a very simple equation. Give you an idea, everything. I just got a little bit taller, and the chair just got a little bit smaller. By definition, because my skeleton, my joints, everything is a structure. This is a structure. Now, it didn't move very much, but by the definition of how things work, it's definitely happened. And I just got shorter. And if you stood up, or actually pretty much I'm definitely the heaviest person in the room. If anybody else stood up, they would have proportionally deflected, gotten less short than me, because I'm the heaviest. So that's something to remember, is everything abides by this rule. That's what this is showing. That spring constant can be kind of hard to wrap your head around, though. It's a very engineering term. So let's pretend, the other thing is we said, well, Medio's heavier, so he deflects more. We're going to assume everybody's bones are the same stiffness. That some of us don't actually have stiffness of slinkies, and some of us have stiffness of these door stops. Okay? So the higher your stiffness is, the worse, the more you have to pull on something. And luckily for you guys today, because I am in town and traveling, I brought my gym with me, and I can actually show this. Does anybody know Tom Brady? American football player?
No, first.
He does. He's a big fan of working out, not with weights, but with bands. So I work out with these in the hotel room in the morning. And you might think that looks like a sissy thing, but it's way harder than using weights. And it's way better for you. So to give you an idea, pass these around. Just remember, because we'll use these a bit, this is a little bit easier, right? This gets a bit harder, and then this gets even harder, right? So it's all just the same material, but it's the idea of we're actually, by adding thickness and more material to each one of these, we're going from this kind of slinky to something that's a bit more hardcore, all right? We'll just leave these out here. We might do a bit with that to show you guys some of these. So when we start mixing and matching things together, we have to remember that we apply loads to our structure, they go to the ground. The way they go to the ground, the path that they take through our structure is completely dependent on stiffnesses. So everything that varies from this guy to this guy, make it a bit more. Oh yeah. That guy, and that guy, right? So one of the key things a structural engineer needs to be able to do is understand that. Understand that big time. So let's say, for instance, can I have a volunteer, please? It won't be hard. Great. Hold this one.
Get out of the way.
Okay. These things can extend twice their length before they snap. All right, so you pull on me. I'm not. You're the one who's going to let go. Look how I'm holding it. Okay. Hold it a bit. Yeah. Okay. Now you take a step back. Now, which arm is working harder right now? Right? You're really struggling, actually. Okay? It's the exact same thing that's going on right here, right? Her hands, just hold, if you guys look, just hold them like this so they can see. All right, her hands are right next to each other, so the deformation of both these things are exactly the same. So right now, you take a step back, you should control the force. Right? Keep them the same. Right? She's having to struggle big time to keep it the same because this one has a maximum resistance of like 60 kilograms. This one is like 5. Right? So if she took a step, thank you so much. So we can do the math, right? If she took a step, if it says 1 meter's worth of deflection gives you 60 kilograms, 1 meter's worth of deflection gives you 5, right? And she stepped back 10 millimeters or something. By that equation, we can actually figure out what goes where. And obviously, it's very much something that this guy goes, no, I can handle it. I'm going to take that for you, right? That's huge, right? Because that depends, it's not just, going back to what we talked about before, it's not just that we have tension and compression, because these guys, what we just did was tension. These guys are pretty bad at compression, right? We could play that game all day in compression, it's not going to matter. But a lot of times we deal with bending in what we do, and you have a horizontal structure that's only supporting 4 points. It's a bending problem more than anything else, right? And that, to do that with these guys, kind of have to double it up, right? But that shows you again, now can you imagine trying to play with this? And I tell you to try and, make this extend. That's why we break the pen by bending, because look at that. I can deform it like crazy in this direction, but in this direction, I don't care if we all work together, that's not going anywhere. So, it's opposed to, I think some bad engineers would walk in here and try and tell you all about that. With the Engineering 101, this is what we get in our second year. And I know that looks scary. So, but it's nothing different than what we've talked about, right? We can kind of see if I put the arrows on here, P is right there, deflection is right there. So everything else must be the stiffness, right? That's all there is, right? So in this situation, we're saying the function of stiffness, the relationship between how much we have to pull and how much deflection we get, is the area times some fancy constant, which you don't have to know about, versus the length. And this is the big thing. This is where it comes into you guys, because you guys control this. You guys want to control this, but to be honest with you, we control this because we don't control E. We can, but really in structural engineering, as much as we want to act like we're fancy, we only have two materials that we really use, concrete and steel. So we're not like geniuses when it comes to actually playing with the variables that we have, right? So I want to stress this to you guys because the L is really in your guys' court. And I want to try and get you guys the scale of when you play with the L, what it does for different, what's called degrees of freedom, right? Because what I just showed you is for the situations of compression and tension. And let's just stick with tension because compression's a bit more difficult because things can buckle in compression, but they can't in tension. But in bending is where we see a lot. We see a lot of stuff bending. We're standing on floors that bend, right? The table is bending because we have stuff on top of it. Engineers have all these tables that sort of give us the exact same equations that I just showed you, right? That they relate the force that you put on something to the deflection that you get. And what is that ratio? It's the stiffness. So the stiffness of the bending is a bit different of equations, a bit more involved. Let's put them up next to each other. Anybody notice any difference? What's the big difference that you guys control mostly? L, right? That L is now cubed, right? So I'll spare you the details of the math and how we're going to get to this direct comparison, right? But effectively, if you do the math, what you'll see is that actually this stiffness right here is something that's a lot less stiff, right? Sorry. So if we say something that bends is actually a fraction of something that is actually driven, right? Bending, actually driven. What does that actually come out to be? It's already a factor of one. It's already a quarter less stiff. Plus you have this L squared. Let's throw out the quarter because let's focus on L squared. We have to think exponentially now. And when you look at something that's exponential, this is why structural engineers cannot sometimes get ideas across to architects because we don't speak the same language. You doubled the length, you didn't just double the problem. You made it 4 times as bad. It's exponential. This typical statement of if you took 30 steps, you'd end up at the other side of the room. But if you took 30 exponential steps, you'd end up at Mercury, almost at the surface of the sun, right? So as you guys were talking to me and we're looking at it, and you're talking about, the precedent is this. Yeah, but we are twice as long, so that's already 4 times as bad. We have more load, so that's adding, and it's adding exponentially, right? Doesn't mean we can't fix it. It's just the idea of when we get to that point where we say, well, it's actually going to be a meter wide tubes. That's where it comes from, because we get there quite rapidly in a nonlinear system. If you guys have ever seen transfer structures up close, have you ever wondered why all of a sudden something that's that width ends up being this width? It's that problem. It goes really back to, we've had something that was in compression, something that's in bending. And the second that you have that, you start to accumulate material, right? So this is why a lot of times you'll hear engineers saying, let's get a better structural system that has less onerous spans. Let's try and make this structure, for instance, something that's a complete arching structure, something that doesn't have to actually bend, but rather is completely in compression. Just to show you the scale of things, again, on one of my projects, this was a transfer structure that I designed, and you could see the level of involvement. Just to give you an idea, that, if you ever see that in reinforced concrete, those are the reinforcement bars, is never right. There's no way that is correct, but there's different project constraints that you always have to deal with. These are bars that are this thick, right? And there's 7 layers here and 3 layers here, all coming from the columns that are not even close to the same, right? So that's the effect. I think that's why I want to get that out there right away, explain to you guys the rules of structural engineering, and why, when we go through this, what's going through my head in terms of, can we get onto that good side of exponential and not be suffering from the bad side of exponential? So that's really, I think that's all I got for you guys. And then I have more stuff for tomorrow, but for now, that's the intro, Structural Engineering 101, so we can communicate. Thank you.